Alright, let's talk about acid-base reactions. So, first thing we need to know about acid-base reactions is we talked about the Svante-Arrhenius definition for acids and bases a little earlier in the unit. Now we're talking about the Bronsted-Lowry definition. The Bronsted-Lowry definition basically states that acids are proton donors and bases are proton acceptors. And that definition, the whole thing there is that it's focused in on the activity of the acid and the base, not the fact that it's in some sort of solution. Okay, the Arrhenius definition is limited by the fact that it says it's in solution. When the strong acid reacts with strong base, your net ionic equation should be this: hydrogen ions and hydroxide making water. When you have a weak acid, and a weak base is the opposite of this, you keep your weak acid intact on the reactant side because it doesn't ionize fully. However, since you're placing it with a base, strong base in this case, you should expect every hydrogen to be stripped off, and so for products you should have your conjugate base there in ion form. Neutralization reaction is an acid-base reaction in which the acid and base react completely with one another without excess. Now, neutralization, the goal is not an easy one to reach, so we use a process called titration, volumetric analysis by titration, to equalize the amount of hydrogen and hydroxide ion in the solution. So we use a standard, a known concentration, and we use that to titrate the analyte, the thing that's unknown. We use a burette setup to do this. In this particular setup, we have a burette and a flask. We might have a stirrer. We might be, instead of using some sort of a color indicator, we could use a conductivity indicator. We could use the production of a precipitate, all kinds of things. So you can titrate many ways. It's not just acids and bases. The titrant's the thing you know the concentration of. It's usually in the burette. Your equivalence point or stoichiometric point is a mathematical point at which just enough titrant's been added to react perfectly with the thing being ionized, or being analyzed, pardon me. So at this point, at the stoichiometric point, you have virtually zero reactant left, and you have all product. The indicator, we can use a chemical indicator of color that will change color at or near the stoichiometric point, and the point at which that indicator changes color is called the endpoint. The endpoint refers only to the indicator's color change. The equivalence point refers to the point at which your acid and base, or your things being titrated together, react perfectly in quantity. So in an acid-base reaction, say we did a titration on this system. We had 54.6 mils of 0.1 molar perchloric acid solution required to neutralize 25 mils of sodium hydroxide solution of unknown molarity. What's the concentration of the solution? The first thing you need is the balanced reaction. And once you have that, you should note that you have equal molar quantities of hydrogen and hydroxide in the system. Okay, in the reaction. That means for every single hydrogen ion, one hydroxide ion is needed to make water. So how do we determine the concentration of sodium hydroxide? The way you do this, to get yourself out of the habit of potentially using a dilution type math to solve this, is to always start with the volume of your titrant, the thing you have the known volume of. If you then multiply by the molarity, you're going to have the number of moles of your acid used. And if you know the moles of acid used, you can extrapolate the moles of base used, and then calculate anything you want. So always start with the volume of the titrant, multiplying by molarity to get moles. This is what it looks like. Volume of the titrant converted to volume in liters, multiplied by the molarity, and then we can convert the molarity of acid to multiplied by molarity to get moles, and then by the mole ratio to get moles of the base, which gives us the number of moles of sodium hydroxide there. Then dividing by the volume known, we have a molarity of 0.218 molar sodium hydroxide. The next reaction type is oxidation and reduction. We call them redox for short. Governed by electronegativity in atoms, and molecules, is the attraction for shared electrons. Most electronegative elements we know of: fluorine's number 1, oxygen number 2, then nitrogen and chlorine. You can use the mnemonic phone call if you like. These are most likely to gain electrons and become negatively charged in a reaction. The rules for assigning oxidation states: elements, all monoatomic and diatomic elements, have a charge of 0. Oxidation state of an element in a bond is going to be the charge of that element in the bond. This is something we'll have to figure out. We'll have some knowns and some unknowns. But sodium chloride We would expect chlorine to take a single electron from sodium, and this be your resulting charges. Sorry, +1, -1. Sorry for the handwriting. Oxygen is -2 in covalent compounds, with the exception of peroxides. Peroxides are -1. Hydrogen is +1 in covalent compounds, -1 in hydrides. Hydrides are relatively rare. They do rarely happen. An example of a hydride, sodium bound to hydrogen. This is usually, it's going to be an alkali metal with hydrogen. It's the only way it's going to happen. Fluorine, +1 in compounds. -1 in compounds, always being the most electronegative element. It's always going to gain an electron, fill its shell. Sum of oxidation states in any compound is 0. Guess what? The charge on carbon dioxide is 0. The sum of oxidation states in an ion is the charge of that ion. So, nitrate, -1. We're going to use our little rules now to look through these. So, bear with me here. In the first, dinitrogen monoxide, oxygen's -2. We know that the sum charge of this molecule is 0, so each nitrogen must be +1. Phosphorus tribromide, bromine must be -1, most electronegative. -3, phosphorus must be +3. Hydrogen phosphite ion, oxygen -2 for an overall -6. Hydrogen +1, covalent compound. Phosphorus, if the whole thing's equal to -2, then phosphorus must be +3. So 4 plus -6 is -2. Tetraphosphorus hexoxide, -2 gives us -12. This must be +12. So +3. How I get +3 there, I have +12 and 4 of them. 4 atoms making a +12 must be +3 each losing 3 electrons. In the amine ion, we have hydrogen always being +1. So overall it's +2. So if it equals -1, there's our symbol there, and it must be -3 for nitrogen. So we can now use our selector to confirm. Got it. Got it. Got it. Got it. Got it. Okay. It is possible to have non-integer states as far as the overall charge is concerned, but this is really an example less of iron being weird than oxygen being able to pull electrons wherever it can and make things stable. Each oxygen is -2 for a -8. So now you have 3 irons who need to make a +8 charge. And no, this is not 3 irons making a 2 2/3 charge. This is 2 irons giving 3 electrons and 1 iron giving 2. These are both common oxidation states for iron, so it's not that unusual to think that this is very possible. This stuff's called magnetite. You may have heard of it. Oxidation and reduction. Oxidation is loss of electrons, giving electrons away. It's an increase in oxidation number, meaning it becomes more positive. Reduction is gain of electrons, decrease in oxidation. This is becoming more negative. Oxidation is loss, reduction is gain. Here's a couple of mnemonics for you to play with. Oil rig and Leo the lion goes grrr. Never seen a lion go grrr, but why not? Oxidizing agent and reducing agent. I want to preface this by saying this will not appear on the AP exam. However, for completion's sake, we feel like we need to mention it to you so you're not completely in the dark in chemistry in the future. Oxidizing agent is the electron acceptor, the thing accepting electrons. So it sounds like that's the thing being reduced. You would be right. Reducing agent, the electron donor. Hey, that's the thing being oxidized. Correct. So we get 2 terms for the same thing. That sounds why they probably took it off the AP test. So at this reaction, we have a redox reaction. We have potassium iodide and fluorine gas. So you're bubbling fluorine gas through potassium iodide. What's going to happen? Well, took the liberty of adding these oxidation numbers in for you. What you should notice is that fluorine is going from a 0 charge to a -1. That's reduction, gaining of electrons. And you should notice secondarily that potassium is going from, not potassium, sorry, iodine is going from -1 to 0. So that's, I'm sorry, Fluorine's being, let's get this right. Iodine's going from a charge of -1 to a charge of 0. That means it's lost an electron. That's oxidation. That's the fluorine again. Iodine is -1 here, it is 0 here. -1 to 0 means it's gained, sorry, it's lost an electron, become more positive, so that's oxidation. Fluorine is 0 here and -1 here, that's gain of an electron, that's reduction. So oxidized iodine, reduced fluorine. Your oxidizing agent is the substance in the reaction that's being reduced. Your reducing agent is the substance in the reaction that's being oxidized. These are always going to be reactants. Another reaction, we have lead oxide, lead 4 oxide, sorry, lead 2 oxide, lead 4 oxide becoming lead 2 oxide with oxygen. So you should notice oxygen has two actions here. No change there, and then -2 to 0 here. That's loss of electrons times 2, right? So we have oxidation here. Lead going from +4 to +2. That's gain of electrons, that's reduction. So lead's being reduced, oxygen's being oxidized. Your lead oxide is both your reducing agent and your oxidizing agent. Okay? It's your thing that's being reduced and oxidized. Interesting, huh? Finally, balancing redox reactions by the half reaction method. Redox reactions, you might say to yourself, I can balance. I don't need to have a special way to do it. Really, you do, because more the way it's been presented to you. I'm going to go first to a reaction, and then we're going to flip back at the rules. We're only going to do one of these, by the way. There's 2 in your notes. There's 1 here. In this reaction, we should see we have this substance becoming this substance, and this one becoming this substance. You should notice nothing looks balanceable here. You should notice you're missing atoms altogether, and there's no perceivable logical way to balance them out. So what we have to do is some manipulation and make some inferences and assumptions that are all valid, and in order to balance it. So we have the dichromate ion becoming chromium 3. Okay, well, I'm going to tell you right now the charge on this chromium is +6, and this is +3. And the charge on carbon here is +2, the charge on carbon here is -2. Okay, so stick with me here. +2 to -2, that's gain 4 of electrons. It's reduction. +6 to +3. +6 to +3. +6 to +3. None of this makes sense. So what we need to do is balance it. Okay? So we should note here that we can separate these into 2 half reactions here and here. And that's what we're going to do. Okay? So let's go back to the steps we need to take. Step 1. Write the skeletal half reactions. So you have half reactions given to you already. All you need to do is separate them out. Balance all elements other than oxygen and hydrogen, if you can. Okay? Then you're going to balance oxygen by adding water, hydrogen by adding hydrogen ions on both reactions. 2 separate reactions. Okay, guys? So you have 2 different reactions. One happening over here, one happening over here. You're going to add, balance everything you can prior to adding oxygens and waters and hydrogens in. Balance everything you can first. Then you'll balance oxygen imbalance by adding water to whichever side needs it. You'll balance hydrogen imbalance by adding hydrogen ions to whatever side that needs it. Okay? Then you'll balance charge by adding electrons to the more positive side. So whichever side is more positive, you're going to add electrons to the side that's more positive in both reactions. Then you're going to make the number of electrons lost equal to the number of electrons gained by multiplying the half reactions by an integer. Okay, so the whole reaction on one side may get multiplied by a number in order to make lost electrons equal to gained electrons. Then once you've got that, you add everything together. Cancel anything that appears on both sides. Special case scenario. If the reaction says that took place in a basic solution, you would add an equal number of hydroxides to both sides of the reaction to cancel out any free hydrogen ions. Once they're canceled out, that makes water on the side where there's hydrogen ions, and you can cancel waters then if necessary. Then we'll check that charge and masses are balanced and be done. So here's what it looks like. So we should notice first we need an extra set of chromiums over here to get 2 chromiums on both sides. You don't have oxygen over, there's nothing to balance. And this one's already balanced on everything but oxygen and hydrogen, so the carbons are balanced. So on this side, because we're short an oxygen On this side of the reaction, we add a water. On this reaction, we're short a whole lot of oxygen, so we have to add 7 waters. Okay, so we balanced everything that has to be balanced. We added oxygen or waters because oxygens weren't balanced. Then we add hydrogen ions where there's hydrogen imbalance on both sides. This one required 14 hydrogens, this one required 4. And now we've got oxygen and hydrogen balanced. Then we add electrons to each side of the reaction in order to balance out loss and gain. Okay, so this is going to take you going through and checking oxidation numbers on everything in the reaction to see where I need electrons and where I need electrons on both sides of the reaction. So then that gets us to the point where, okay, in this one I got 6 electrons here and 4 electrons here. So 4 being lost, 6 being gained. Then, how do we do that? 6 and 4, what do we multiply by common factors to get? Oh, okay, well I can, common factor 12. Okay, good. 3 times this whole reaction, 2 times this whole reaction gives us this gigantic reaction, which we can then add sum up, and we can simplify. So these numbers here were simplified, and then we end up getting, after all the cancelings, this balanced redox reaction, which you should now say to yourself, yeah, there was no way I was going to do that. We'll practice this as a group in class. Do not feel like this little session was supposed to get you where you're going to be an expert. It's been fun. We'll see you on the next one. We'll be in chapter 5 before we know it.